Please go and download the latest version for your reference. And the things which I have changed is that in the example number 3, the formula we had last week, I had integration here instead of summation, which was wrong. So I changed the integration to summation, but the rest is the same as before. And another thing which two of you told me last week, it might be a mistake there, and it was, is that here, instead of 1/6, it should be 1/16. So I missed 1 here. So just keep in mind that this part should be 1/16. Still, you get this number as a result, but it was a typo here. Okay. And select your preference, and later today or tomorrow I will select the most voted one, and I will book a room for it, and then write an announcement again in Learn for new date, the selected date with the room number. Okay? Yes?
Is it on purpose that it's only the last week before the exam?
Actually, I have another course beside this which I cannot do it in week 17 as well, so I have to schedule both of them, and that's why I selected this week for. But you know, the last week in this course, this lecture and also a lecture which we will have on Friday, both days are exam preparation, so you will not learn new subject, but I will ask you to solve one or two of the previous exam sets in these 2 days, so you will not learn something new. We just will solve some exam examples. So don't worry about the topics. Any other question? Okay. But if you have not done it, please go and fill out this. Let's move to today's topic. The original plan was just to start the Fourier transformation, and this slide was the outline. However, if you remember last week, we couldn't cover the last part related to periodic functions. So that's why first we cover that one, and then we go through these bullet points. So let's assume we have an LTI system. You know what are LTI systems, and you have seen them in Laplace lectures as well. But now assume we have a system which now the input of the system, which I called it S of t, is a t periodic signal. So it's a periodic function with the period of capital T. And as you know, any periodic function can be written in a harmonic oscillation form, which can have a format like this one. A0 is C0. You have seen it before. For AN, we have a formula which you can have and put it there. And omega is radian frequency, and phi is a phase, which is the argument of your coefficients, Fourier series coefficients. And then in a frequency domain, we have a transfer function of h of s for such a system. When you run any system, no matter it's a mechanical, electrical, or anything else, we can say that the output of the system, if I want to show the output, or sometimes sometimes we also call it the response of the system. It usually consists of two parts. I will give you a very simple example. Assume you want to go to the 4th floor of a building. So your desired output or response is that you want to go and reach to this 4th floor. Then you push the 4th floor button, and then the elevator of course moves. And then maybe you have some response, something like this. Of course, it takes time to go from 1st floor to the 4th floor. Maybe say something like this. And then you are at the 4th floor, or maybe very close to the 4th floor. This part of the system, which of course takes time to reach to your desired output or response, we call it the transient response. Transient response.
So you push to number 4 and you get, what was the...
This is the response, or how the elevator will move from 1st to
okay.
1st floor to the 4th floor. And this is an example. Any system, electrical, mechanical, of course, it takes time for a system to reach to your desired output. And then the one which is close to your desired output, this is called, which we call it steady state part of the response. They have other names as well, but for now, let's look at it like this one. So any response, any output of the system is a combination of the transient part and the steady state part. Of course, depending on the nature of the system, it's very important to have very specific transient part, because for instance in the elevator, it cannot move very fast because it will sacrifice the safety of the people. It cannot go very slow because it sacrifices the patience of the people. So always it should have some specific structure, or it should follow some specific things. But generally, all are consist of this. In this course, and for this part of the course, we will assume that somehow this transient part will happen so fast, such that we can assume it's not there, it's almost zero. And just for now, and this part of the course, we will assume that when we have a system with a t periodic function as an input, the output is only consists of SS, which is short term for this steady state part. Okay? And if now you want to find the output of the system, which is the same as the steady state output, this is the formula you have to use to obtain the output. How we read or obtain that? Here we have H0. For this LTI system, we have H of S, which is the transfer function of the system. When you want to find H of 0, just put at S equals to 0, and then you have it. So it's not difficult to find this one. And also A0, this is from your input signal. This is from here, A0. Then plus this summation of n equals to 1 to infinity of absolute value of h of I n omega. Again, h is your transfer function. And now you need to find the absolute value of h of I n omega. And omega is your frequency. So it's, again, you can obtain first this term and then take the absolute value of it. So this part is also doable. We can do that. Then we have an, which is again from your input signal. We have it from previous slide. Cosine of n omega t plus phi n. Again, this part we know it from input. Plus the argument of h of I n omega. So if you obtain each individual term and then put it together by using this equation, then you have the steady state output of a system. Let's do one example. I call it example 0 because it's not related to Fourier transformation. So now we have a LCI system with this differential equation. So this differential equation is given. First, we need to determine the transfer function. I think, yes, please.
I just have a question about the formula on the previous slide.
Yeah,
because we still have the n variable, which we use. Is it in the same way as we use it in Fourier transformation, where it adds up to the function being more precise? Or what's the
here, yes,
it
is. Yeah.
Right. So you can actually, so when you say, the summation, this,
the
it
input,
can be several.
The input is periodic. So you give an input to the system which is periodic, and you can see we add these n's such that it becomes the good approximation and for the input signal. Am I right?
Yeah.
This also happens for the output part. So if we do this summation and add this together, then you have much more precise or accurate output as well.
Right.
Yeah. Any other question before going to the example? And if you raise your hand and I can't see you, just call my name, because I don't want to go ahead and then see you after 5 minutes. Okay, so here first we need to define the transfer function. I think hopefully all of you know how you do that. And then we need to find the y of ss of t. When the input signal is this, so the input signal is a periodic signal, as you can see, and it has this structure. So we have A0 and then some other terms. I will give you 5 to 7 minutes time such that you try it yourself first, because we have a formula and everything. And after that, we solve it here together. So 7 minutes from now. Differential equation is given, and now we want to find the h of s. So for part 1, we know that we have to take the Laplace from both sides of this equation, and because nothing is mentioned about the initial value, it means all of them are 0, as you know. So it will become s capital Y of s plus half of y of capital Y of s is this one. And now we do a factorization of capital Y of s plus half. And from here, the transfer function would be 1 over s plus half. Are you all agree with this? Okay, that's perfect. Now, before going and obtaining output, let's look at the input signal which is given there. We have the form of x of t there. Let's compare it with the general form of the t periodic input. If you compare the x of t we have in a screen with this one, what is the upper limit number which we have there? It's not till infinity, as you can see, because we have only a couple of terms. So what would be the maximum, the upper limit here? Can anyone tell me? By just comparing, you should be able to identify that. Yes, please? Exactly. Why?
Because that's 2 terms.
It is 2 terms, and also we know that it is n omega t. So let's see here. You have 1 pi t, and here you have 2 pi t. So you can see just by looking, the the upper is 2, and also omega is pi in this input signal. Another thing which I want to do is that, let's go here. The phi n, which I have in the input, I also can use it, or we have to use it in the output as well. However, in the input signal we have there is here we don't have any phi, so it's 0. But the 1 over 3 minus let's look at these terms only for now. We have cosine of pi t plus pi. Again, we have a formula which we can use, and it is in additives of the book, which, if I remember it correctly, it is cosine of a plus b is equals to cosine of a cosine of b. I should check this one, which is plus or minus, then sine of a sine of b. Let me check this part because I'm not 100% sure about the formula. And if you know the correct, also you can tell me, but
Isn't it a minus?
and it should be minus. Yes, thank you. So that's why I was not sure. Okay. So our A here is pi t and B is pi. So if I use this one, I mean this here, it will become minus pi over 2 cosine of pi t cosine of pi minus sine of pi t sine of pi. What is the sine of pi?
One.
No, 0.
0.
0.
You know, this is the cosine axis, and this is sine, and the sine of pi is 0. Okay? So this term will go away. And what is the cosine of pi?
1.
Minus 1. So this is minus 1. So this again becomes minus times 1 minus I have here as a plus 4 over pi 2 cosine of pi. So now you can see I don't have this phi here anymore, and of course the sign should be changed. Now I will use this new x of t to find my y of t. So first, based on the formula, here I need to have h of 0. So I will compute each term first, and then at the end we can add it together.
Yeah.
Yes, please?
Where did the 2 go in the sign?
We don't have 2. Where is 2 here?
In cool.
Here?
Yes.
We have not done anything here. Whatever we did was only for this part.
Okay. Okay. Yes.
Yeah, so it is there.
Yes.
So now we need to find h of 0, which means I need to find h when s is 0. So I have h of s, and if I put s equals to 0, it will become 1 over half, which is equals to 2. I think it should be 2. Yes. Another thing we need is a0. We can read it from here, and a0 is equals to 1 over 3. Are you all agree with it? Just compare this general formula with our x of t, and we can see it's 1 over 3. Another thing we need is here, we know that the maximum summation which we have to go here is n equals to 1 to 2. Why? Because the input is also from only 1 to 2. So it will be the same here. So first, I will need to find h of I n omega for n equals to 1 and 2. So h of I, let's say for n equals to 1, n is 1 and omega is pi. And also for n equals to 2, I need to find h of I of 2i pi. Yes, please.
Yes, I can see why n is equal to 1, but why is it that it's equal to 2?
Because again, we're back to our x of t.
Yes.
And here, when we did the comparison, we found that the first term here is when n is 1. And another term we have there is for when n is 2. So this summation here starts from n equals to 1 and goes to n equals to 2, and it is a stop there.
If it's a 3 there instead, would it then have been
If
n
it was the 3, for instance, then it should be another term here.
Oh, okay then.
Because it is the summation, so you should add up each term together. So if n goes to 4, it should be another summation here.
And then it would
As
have been
well.
n equals to n to 1 and then n equals to 4.
Then it goes from, then the summation here goes from n equals to 1 to 4, for instance, and so on.
Yes.
What if we've done some Fourier transformations where we had like even and uneven numbers, so we would only do like the uneven numbers because even numbers would be 0.
Then, yeah, maybe you have a case
So it could
that
be 1 to
some
3.
of the terms for evens become 0. Then you have, for instance, n equals to 1 here, n equals to 3 here. Then you can say that it goes from 1 to 4 because the fourth one is also 0. Because 2 and 4 and 6 and so on are 0.
Alright.
Can you follow me?
Yeah.
Good. So,
How did that become 0?
how it can be because there is possibility. I don't have an explicit example in mind, but sometimes, like I think we had it last week or a week before that, which for some of the n's, the Cn was 0. Some of the odd groups or even groups. Am I right? Then when that one is 0, then the Cn is, because you know this an is 2 times absolute value of Cn. This is the formula we had it before. Okay? Then if for odd n's this Cn is 0, automatically an also becomes 0. Then in this summation for those specific terms, the whole 0 times this cosine is also 0. So that's why some of them become 0.
Yeah. Okay. Yes.
Good. Okay, now let's back here. Now I want to find the h at I pi and 2i pi. So we have a h formula, it is here. So it will become 1 over I pi plus half and 1 over 2i pi plus half. And I need to take the absolute value of those as well because it's in the formula. Before taking the absolute value, something which I do, which I think it helps me, is that I try to get rid of these decimal point values I have here. So what I do, I multiply and divide this by 2 over 2. So technically I do it by 1. Then it will become 2 And for the other one, I do the same. So I multiply by 2 divided by 2. So it will become 2 over 4i plus 1. Now I take the absolute value of 2. I need to have, again, for n equals to 1, the absolute value of h of I pi, which would be the absolute value of this. The absolute value of 2 is 2, and then the absolute value of some complex numbers, which would be square root of 1 minus 4 pi to the power of 2. And for n equals to 2, if any part is not clear, just ask. Yes, please.
Okay, so I am following with the numerator. The absolute value of the numerator is 2, but the denominator I'm not exactly following.
Okay, this is a complex number, so I call it as a plus bi.
Yes.
When you have a complex number, the square root is a to the power of 2 plus b to the power of 2.
Oh.
So let's use this here.
Shouldn't it be 1 plus 4 pi squared?
Then,
Yeah.
did I mean a minus then? Yeah, it should be a plus, you're right. Then it is this one, because it is 1 to the power of 2. I to the power of 2 is minus 1. And that's why it will become minus then. Let's see.
But
They
but the formula is not taking, it's not squaring the I, because the
Oh, yes, you're right.
It's the
Yes.
distance, it's the length
Yeah,
of the vector.
yeah.
So-
Only we look at the 2 pi.
Yeah.
You're right, not I, because yeah. Then of course it should be plus here as well. So it is 1 to the power of 2 plus 2 pi to the power of 2, which is 4 pi to the power of 2. And this one is the same. Yeah. Good. Any other question here? Okay. Let's look at the formula one more time. We have x0, a0. We found this absolute value. For an, we can find them again by looking at x of t. We have this as an for n equals to 1, and this one for n equals to 2. Again, just by comparing this with this, you should be able to recognize or identify that. And then the only term which I missed is the argument of this. So again, here, I need to find the argument of 2 over, I have it here, 2i pi plus 1, 2i pi plus 1. Or for the other one, we need to find the argument of 2 or, yeah, 2 over 4i pi plus 1. Again, Maple can do this for you, but if you want to do it manually, I have a formula here. Which it says that when you have the argument of such a rational function, it's always this equals to the argument of 2 minus the argument of the denominator so 2?
0.
Exactly. So this becomes 0. And now I want to find the argument of 2I pi plus 1. We have another formula for it, which is here. Which, for a case, which we have the same case there, the argument of x plus iy, if x is positive, is always the arc tangent of y divided by x. So I use this one. It will become 0 minus, it is minus arc tangent of 2 pi. I use the same approach for this one. Becomes again argument of 2 minus the argument of 4I pi plus 1. The argument of 2 is 0. And for this one, I use the same formula which is there. It will become minus arc tangent of 4 pi. Yes.
I got a question.
Yes?
Couldn't you also, because you have brøken, I'm not sure of the English term.
Fraction?
Once again?
Fraction?
The fraction.
Yeah, rational form.
Yeah, but you could also change the fraction to in a rectangular form.
If it's easier for you, you can do that. For me, this approach is easier.
Alright. Yeah,
As far as the results are correct, you can use other approaches. as
yeah,
well.
because then you can transfer it.
Yeah.
And then you can.
Yeah.
Right. Yeah, I'm just make sure that it would
Yeah.
be possible to do that approach.
But as I said, maybe at exams, the easiest is to use Maple to do it for you. You save time.
Yeah.
For everything you have learned in other math courses, you can use Maple. And you have not learned this argument or integration or differentiation from me, so you can use Maple for those. And I will make this clear later on when we do the exam preparation as well. Okay, now we have everything. Then you should bring all and put it together. I have not done it because it was too much typing for me. But you should grab everything we have on board and put it in their places here. And then you are done. Any question?
Can we just do it on the board?
I can write it here, yes?
Yeah,
Let's
just
do
to
that.
try to get all the.
Okay, then you can also take a picture of it and have it.
Yeah.
1 S of t is h0, which we found as 2, times a0, which is 1 over 3. Let me put a line here. Then, plus, now I go for n equals to 1 only. Maybe I write it here. Then I have this absolute value of h of I pi, which is this one. So 2 over square root of 1 plus 4 pi to the power of 2. Another term I have is a1, which a1 is 4 over pi 2. Correct? Yes. So times 4 over pi to the power of 2. Then cosine of n is 1, omega is pi, so it would be pi t. Am I right? Yeah, but I'm not done. Phi is 0, but now I have to have this argument, which is minus A2 is 1 over pi 2. So 1 over pi 2 cosine of 2 pi t, phi we don't have it, minus r tangent of 4 pi. Let me double check everything. I think it's correct now. Yes, that would be the whole result. Complete result. And maybe you want to take a picture of both before going to the Fourier transformation.
Ja, A1, den kan man læse ud af anden del. Det er A1, det bliver over pi anden, som er bevægt ud af x og t. Jeg er ikke sikker på, at
Okay. Now let's